Okay. Can you see my screen, my slides?
Yes, yes.
Okay. Good afternoon, everyone, and thank you for joining us for this webinar. My name is Morteza, PhD student at Technical University of Denmark, Team by Engine group. And now I'm going to talk about some of the research done by our group, which published in popular journals and all are in the field of self-healable sensor for wearable devices. And in this presentation, I'm going to talk about flexible sensor in wearable devices, which is one of the main focus of our group. And after that, we will talk about self-healing mechanism and some of the self-healing materials, and we will go deeper on the hydrogel systems. And we will finish with reviewing some of our material systems, which already published. And let's talk about the flexible and wearable electronics. Nowadays, with the virus revolution and technology miniaturization, electronics have found new application in the form of flexible, wearable, and monitoring purpose. Ongoing research on wearable electronic system has resulted in a number of prototype garments that can monitor and rely various type of data from a human body. Flexible physical sensor comprise two distinct building blocks. That is the flexible template material and the active sensing elements, which may take either solid or liquid state. The fundamental sensing mechanism of the flexible and wearable sensor is based on the mechanical deformation experienced by the sensors, such as pressing, stretching, bending, or even twisting. And as some of the application of the flexible and wearable device in healthcare and biomedical fields, we can mention artificial electronic skins and physiological monitoring and assessment systems, and therapeutic and drug delivery platforms. And sorry, it's not working good. And flexible and wearable devices based on a skin-friendly, soft, elastic material can be easily attached to the skin of the human. And so that a series of vital health information, such as wrist pulse, body temperature, and blood glucose can be extracted and analyzed to help the patient maintain physical fitness. Here you can see the most common type of wearable electronics for monitoring human health information, including force sensor and temperature sensor, physiological and biological sensor, and some kind of multifunctional sensor. In recent years, self-healing and stretchable biomaterials have received increasing interest in wearable devices and epidermal electronics and implant and cybernetics. Indeed, desirable material for these applications must be able to blend perfectly with organ and tissue for a long period without any unwanted outcomes. And while at the same time retaining their predefined function and inherent properties, as well as recapitulate some of the mechanical and biological abilities of the target tissue or organ. In this case, self-healable hydrogel are the most interesting material for these purpose. And if we want to start with the hydrogel, hydrogel are composed of polymeric networks that are capable of absorbing and retaining a high amount of water. And however, as one of the fascinating properties of natural tissue in their ability is their ability to self-heal after minor injuries. To really recapitulate the physical properties of native tissue, such human made biomaterials, also to spontaneously heal and regenerate injuries inflicted on them. This inherent ability of native tissue to regenerate on demand has initiated enormous motivation to develop intelligent hydrogels with with somehow a self-repair mechanism. Let's talk about the self-healing mechanism. Self-healing hydrogel relies on one common principle involving a so-called mobile phase, which enables crack closure through a combination of mass transfer and reconnection of broken links within the hydrogel matrix. And the reconnection within this matrix is typically mediated by either non-covalent or covalent bonds. The non-covalent interactions are based on weak sacrificial links such as ionic or hydrogen or hydrophobic bonds. And while the chemical bonds are based on the dynamic covalent bonds and metal coordination bonds. The combination of the mentioned covalent and non-covalent bonds has also recently been used to generate mechanically tough and elastic double network hydrogels with rapid self-repair properties. And yeah, hydrogen bonds are among the most common non-covalent interaction found in the nature. For instance, in helix structure of DNA, or in folded structure of proteins and many polymers such as cellulose and foods. Hydrogen bonds occur when the positive hydrogen atoms establish an electronic link with the electronegative acceptor atoms, such as oxygen or nitrogen or even fluoride. The strength of the hydrogen bond depends mostly on this negative charge of the acceptor atom and the pH value of the solvent in which the bonding occurs. As an example of hydrogen bonds are those formed between two hydroxyl groups or between carboxyl and amide groups and between again hydrogen and fluorine. And but the most important point here is the strength of the bonding. The bonding strength of hydrogen bond varies greatly from 0.25 to 15 kilocalorie per mole, with the weakest being those formed with fluorine and the strongest those that incorporated hydroxyl or amide groups. Still, a hydrogen bond is several times weaker than ionic and covalent bond, as you see. And when a lot of them are present within the hydrogen matrix. Moreover, the association of and dissociation of the hydrogen bonds occur rapidly, typically on sub-picosecond in the range of picosecond scales. This property is a governing factor behind the rapid healing time seen in repairable hydrogel based on hydrogen bond. And yeah, if you want to talk about the self-healing hydrogels and some polymers, the self-healing hydrogels have so far been made from either natural or synthetic polymers. The natural polymers, you can see some of them are for the most part of polysaccharide-based polymers such as alginide, chitosan, and hyaluronic acid. which we will explain about, we discuss about it later. The synthetic polymer systems, on other hand, are based on polymers such as PEG, polyethylene glycol, polyacrylic acid, or PVA, and polyacrylamide, and these polymers, which provide certain advantage and disadvantage, and abandoning one in favor of another typically involves some trade-off. For example, the natural polymers are typically more biocompatible, as polymers such as gelatin and chitosan are formed for their cell attachment properties, while PVA and polyacrylamide typically yield stronger and more elastic hydrogels at the cost of reduced biofriendliness. Yeah. In the following subsection, let's talk about the double network hydrogel. The working principle behind double network hydrogel is essentially based on a combination of weak and reversible bonds, and also at the same time strong and irreversible bonds. Together, these can yield tough and highly extendable hydrogels due to the dissipation mechanism embedded in the reversible bonds. A prime example of system like this is based on ionically bonded alginate as the reversible part, and covalently bonded polyacrylamide, and as a irreversible polymers. Here you can see the hydrogels can stretch in much more than the electronic conductor, which are ionic. I think there is a crash here. I cannot see it.
We can see your screen now.
Yeah, it freezes here.
It's the double network hydrogels.
Can you see the double network hydrogen?
Yes, yes, we can see.
Okay, let's see. I don't know what happened here. We have two kinds of conductivity, one based on the mobile electrons, and one based on ions. The polymer network makes the hydrogel and elastic solid, and the water molecules make the hydrogen an ionic conductor. I mean, the polymer network has a mesh size of around 10 nanometer, which is much larger than the size of water molecule, allowing water molecules in the hydrogel to maintain the same chemical and physical properties as in liquid water. So, for example, if dissolve salt in water, we can have a mobile ion, which change the resistivity of the water from around 18 megaohm. 18 megaohm is the resistivity of the pure water, and after adding salt and dissolving salt into it, it goes increase to less than 1 O, depending on the type of and the concentration of salt, of course. Here you can imagine how mobile ions and electrons can make a material conductive. And in this case, we are working on hydrogels, ionic material. And mobile ions and ions here and electrons in, for example, in metal conductive material form an electric double layer here, and the interface between between a hydrogel with this and the metal part, and it can help us measuring the electrophysiologically of the brain, heart, and muscle requires and muscle, which requires work based on ions and mobile ions. And here you can see that how the resistivity of the electronic conductor decreased with a small amount of stretch, and because it's based on the mobile electrons, and with a small stretch, the ions cannot move as easily, so the conductivity, the resistivity goes up very fast. And I'm not sure if you can see it. Yeah, let's go back to the hydrogels. One of the ideal pathways for generating a self-healing hydrogels is through dynamic covalent imine and enamine bonds, especially for chitosan. And based on this, there are some research working on the enamine bonding between carboxymethyl chitosan and aldehyde functionalized PEG to develop a self-healing hydrogel. And these two polymers form a stable hydrogel film after 5 minutes with a good storage modulus and healing efficiency ranging from 80% to more than 90%. It depends on the time, and in the biological, physiological temperature. And continues in one of the research done by Team Bioengineering Group. They have utilized a combinatorial and high throughput platform for low-cost development of optimal stem cell delivery systems. They have developed a combinatorial library consisting of many hydrogels made from double bonded polysaccharide-based hydrogel and some multifunctional and two-dimensional nanomaterials, nanosilicates, like laponite, samectone, and Mont. And they see that these hydrogels can significantly enhance the carrier's mechanical properties without increasing hydrogel cross-linking and polymer density to a point that makes them useless for the tissue engineering application due to the associated decrease in hydrogel porosity and hydration degree. This hydrogel cross-link through simple one-step mixing procedure in contrast to many of their counterparts, which are solidified through complex and toxic chemical reactions. And here is the mechanical studies, and you can see a stress strain curve corresponding to the mechanical compression test assay done for hyaluronic acid and alginate and composite, I mean hyaluronic acid and alginate, and with different concentration, of course. 3 cycles run here for each combination. The toughness value were retrieved from the area below the stress strain curve and plotted here as a function of the content of alginate. And the compressive modulus was retrieved from the stress strain curve also by fitting the curve with a linear equation in the 15 to 25 strain region. And they also screened the combinational hydrogel library to identify hydrogels with young modulus with the aforementioned range that would enable significant energy absorption without compromising the mechanical recovery during loading and unloading cycles. Piercing hydrogel were evaluated in terms of compressive modulus toughness and energy absorbing capacity and recovery after 3 cycles of loading and unloading. And yeah, the mechanical studies show that most of the gels broke in the range of 53, around 53 to 56 %. And so they decide to use the nanosilicate material to enhance the mechanical properties and enhance the what you call application of these hydrogels. And yeah, here you can see the stress strain curve for different composites, which composites together with clay and some nanosilicates. And let's go on another. Let me see if we have time. On another paper, it's based on silk fibrine and laponite. You can see a schematic of the silk fibrine and laponite film preparation. In brief, silk fibrine was mixed with laponite to yield a silk fibrine laponite solution that was transferred into a freestanding film through a solvent cast drying. Silk fibrine is a polyamphylate with an isoelectric pH of approximately below 4, around 4, and laponite displays a negative surface charge and a small positive rim charge. And so these two compounds can therefore potentially join into a small agglomerated, making and make it difficult to prepare a uniform and a stable film. Indeed, in these preliminary experiments, they observe a gelification of the SIPO film at acidic pH value, something most likely caused by a more positive charge distribution on silk at lower pH value. And the resultant more intensified electrostatic interaction with the negatively charged surface of laponite. And finally, here you can see the SCM and the beta sheet of the laponite in the silk fibrine matrix. And finally, they tap into the both realms and by embedding laponite into silk-based thin film to generate an ionic conductor that exhibits a host of highly sought after properties in the field. And these properties include good crystallinity and transparency, mechanical strength, and recyclability, optical transparency, and of course, electrical sensitivity. And also it has a chemical and thermal and dimensional, chemical and thermal and dimensional stability in different environments. And here you can see this image shows the transparency, and in UV spectra, we have UV spectra here. And here you can see how it's the TGA test for, for different concentration of the silk fibrine with different concentration of laponite. And And here it's a test for to study the recycling of the SIPO films. And even after this test, it shows the conductivity well also. And for this measurement, they just pick a highest quality film and conclude that SIPO remain mechanically intact after these bending cycles and exhibit an unchanged electrical conductivity. And here it's how it works with the what you call electrical test, and how it works after more than 5,000 cycles. It is still has the same conductivity and or resistance here. And you can see how with bending, how the resistance change in a linear way. And it's so sensitive. It's so sensitive to the bending and the strain, and it's suitable for capturing different data from the human body, and various motion and capture imaging technology are currently used to measure the human motion. But these approach present a number of drawbacks related to their limited measuring range, and also the low sensitivity, and in some cases impractical measuring scenarios. By contrast, flexible sensing system that readily conform to the curvature of the human body can measure motion from any part of the human body in any setting without discomfort for the user. Such wearable sensor can gather biological information from athletes during games, and soldiers in the battlefield, and musicians during concerts, and can help them to improve their performance by helping them to gain the need of mastery of their subtle motion during the strenuous activities. Therefore, in addition to the, you can see here, we can use this highly stretchable sensor for most of the joints in the body, and as a kind of motion sensor. Okay, thank you very much for your time, and I also would like to express my gratitude, thanks to the Bioengine team, especially Firoz and Alireza, because he gave me the chance to find myself in this exciting project.
Thank you so much, Morteza, for your nice presentation. And I'm gonna ask everyone, if you have any question, comment, suggestion, just please raise your hand or